Hello, everyone. My name is Lucier. Today I'm going to be talking about quasi-linear mechanisms for non-quasi-linear agents. This is joint work with Moshe Babaioff, Richard Cole, Jason Hartline, and Nicole Immorlica. So this is a talk about algorithmic mechanism design. And so I'm going to start by giving you a little context for those who might not be familiar. I'm going to do this through a simple sort of toy example that will be a recurring example through the talk. This is a very straightforward allocation problem. I'm going to assume there's some pool of users, right, pink and purple here, and a collection of goods, apple and banana, that the users have value for. We're going to assume the users' values are additive. Okay, so each user has some value for each good. And if you get multiple goods, your value is just the sum of the values for the individual goods. Okay, so the pink user's value for getting the apple and the banana in this case would be 3. Our goal as the designer is to partition the goods amongst the users to maximize some objective, which might be, for example, total value of the assignment. Now, you might notice in this case that that objective is super trivial. You would obviously just give the banana to the pink user and the apple to the purple user to maximize total value of 4. The thing that makes this a little bit challenging is that those values aren't known to us. They're private knowledge to the users. And we assume the users are strategic and might misreport them to maximize their own gains. All right, this is where the game theoretic part comes in. There's sort of a standard mechanism design solution to this kind of problem, which is to charge payments. Okay, so now as a designer, we're not just going to choose which subset of the goods each agent gets, but also how much they pay. And a common assumption is that each agent wants to maximize the value of the goods that they get, which we can now think of as being measured in dollars, minus the amount they pay. All right, this assumption is called quasi-linearity, and you might, hint from the title, we're going to be revisiting this assumption in this talk, but for now, let's just take it as given. Right. Under that assumption, there's a very nice solution to this optimization problem, which handles the incentive problems, which is called the VCG mechanism. In this case, it has a very simple form. What we do is for each item, right, so the agents would declare their values for each item, and then for each of the goods, we would give the good to whoever had declared the highest value and have them pay the second highest value. Right, so in this case, the pink user would get the banana because they had the highest bid of 2, and they would pay $1 because that was the second highest bid made by the purple user. And a classic result for mechanism design is that this particular way of setting up the allocation and payments will incentivize everyone to report their values truthfully, in the sense that no matter what the purple agent declares, right, the pink user will always maximize their gain, right, maximize their utility by declaring their true value for both the apple and banana. Now, this is a specific case of a very general, property of the VCG mechanism, which, holds for a very broad class of allocation and social choice problems beyond just this additive case. And there's now a rich theory within sort of the economics and computation literature that extends that theory of the VCG mechanism to various classes of approximation algorithms as well, right? And it's a beautiful theory. It also has a lot of applications to sort of real markets, right? This applies to online advertising platforms, cloud resource scheduling and pricing, two-sided markets like ride sharing and crowdsourcing. In a lot of these cases, we have a theory of how users will respond to prices that sort of builds on this quasi-linearity of assumption. The thing I want to point out is that this quasi-linear assumption is very crucial, right, to this result. Right, our analysis, which shows that agents will report truthfully, requires that they think about the trade-off between value and payment in this way, and in particular that they have a linear value for money. And I want to note that while this is very standard in mechanism design, it's not uncontroversial sort of within economics more broadly. All right, a more general model is to have the disutility for spending money not necessarily be linear in the amount of money spent, but some convex function of the amount of money spent. All right, what this captures is the notion that each marginal dollar spent buying apples and bananas is weakly more costly than the last, in the sense that it's somewhat more painful, right? It costs more utility. Now, why should we think of this as, why is this reasonable, right? It's like, why do we care about nonlinearity and convexity? Well, this captures various notions and behavioral things that we observe in practice, right? So for example, it captures the idea of hard or soft budgets, right? Users usually don't have unlimited access to funds. And so when they're spending money on your mechanism, your allocation algorithm, every dollar that they spend is a dollar they could have spent somewhere else, right? So maybe they have some disposable income, right? So at first they're willing to spend money up to their value, but then eventually they start spending enough. They start realizing like, okay, if I spend more, then maybe I should skip my latte today. And if I spend even more than that, okay, maybe I'll have to take out a loan to make my rent. And eventually at some point they might be unable to spend more money, right? And so this is like, we can think of this as a convex disutility for spending more. This applies to like to individual users, also applies to firms, right? So you can imagine, for example, an advertising platform, right? When I'm thinking about how much an advertiser is going to spend, well, that advertiser probably has some advertising budget that they're splitting across different channels, right? So when they're spending $1 on my platform, the value of the dollar isn't just $1, it's how much value they could have gotten from that dollar somewhere else. And that might not be linear, right? This also captures notions of risk aversion, right? So you might imagine that the quasi-linear assumption, this linear value for money, presumes that, say, agents would be completely indifferent between getting $1 million for sure and having a 50-50 lottery between getting nothing or getting $2 million. I don't know about you, but I personally would have a strong preference for just the $1 million, right? At that sort of stakes, I'd much rather have that first $1 million for sure, because the second $1 million is much less valuable than the first to me. And again, if you apply that logic to how people will spend money, that would translate to a convex disutility for spending their money. Okay, so our main question is, if we actually believe that this quasi-linearity assumption, while convenient, doesn't necessarily model reality, especially like in certain contexts, what would happen if we took this theory of mechanism design for quasi-linear agents and all of the constructions and best practices that come out of that theory and deploy them in environments where in fact the agents might not be quasi-linear, right? How robust is this theory to non-quasi-linearity behavior that users might actually exhibit? So what do we find? Well, suppose we do exactly that. Suppose we take a mechanism that would be truthful for quasi-linear agents and deploy it in an environment where agents have convex disutility for payments. Now, the mechanism might no longer be truthful, right? The agents aren't even reporting these disutility curves. But it turns out that at equilibrium, the agent can best respond in a way that sort of has a nice structure, right? Agents have a best response where they take their valuation functions and scale them down by a uniform scalar multiple. And that scalar is actually interpretable. It will correspond to the return on investment that the agent is getting at equilibrium. And this applies not just to the additive setting we talked about before, but actually a broad class of social choice problems similar to the set of problems to which the VCG mechanism applies. Now you might ask, we know something about the structure of these equilibria, but like, what happens to these allocations? Like, are they any good? If we restrict our attention back to this additive case, like the example we discussed at the beginning, we can show a price of anarchy style result. Right now, we want to show that the outcomes have good welfare. We have to be careful about the way we define welfare here. We're no longer in quasi-linear settings. Transfers between agents, potentially come at a loss of utility. What we do is we define a notion of welfare we call transferable welfare, which extends the notion of liquid welfare that's used a lot when discussing mechanism design for agents with budgets. We're going to talk more about that definition later, but it turns out that for this notion of welfare, transferable welfare, we show that at any equilibrium of this mechanism, and there could be many, but at any equilibrium of the mechanism, we're going to end up getting at least half of the optimum. We also have a price anarchy style result for revenue as well, but I'm not going to talk about that very much in this talk, but please see the paper for more details about that. Okay, so before going into the details, I want to make a note about related work. There's a very rich set of papers that looks at mechanism design sort of beyond quasi-linearity, where we see agents with different utility models like budget constraints or having risk aversion. Generally, the way these papers work is that you design a mechanism that's targeting a good outcome when agents have this particular type of utility function. We're doing something different here, which is that we're looking at the mechanisms that are designed, that are truthful for quasi-linear agents and asking how robust those mechanisms are when we go into these environments where agents are not necessarily quasi-linear. I also want to point out in particular a line of work that looks at budget-constrained agents for advertising platforms. It turns out that technically is very similar to the sort of results that we're doing. And you can interpret a lot of our technical work as taking these ideas from mechanisms in advertising platforms with budgets and extending it to more general notions of convex cost for spending money. Great. Now let's get into a little bit more of the details of the model. All right. So we're going to have, again, this allocation problem with n agents and m goods. Assume additive values across the goods, like in our example before. Some of our results actually apply much more generally than additive valuations to other social choice problems. But for now, let's focus on the additive case. I'll get to those generalizations later. We'll now have this cost of money curve, which we think of as this convex disutility for spending money. We assume it's non-decreasing, weakly convex. Also, for technical reasons, we're going to assume that there's a lower bound on its derivative, so that there is some disutility for spending money everywhere, which will normalize to being 1. And so now the utility of an agent given a certain outcome will be the value they get from their allocation minus their disutility from payments. So for some examples of these disutility curves, we can capture the quasi-linear case by having the curve be the identity function. We could have Ci of p be some other coefficient times p, which you could think of as modeling a bidder who wants a certain return on investment target. Right, so they would have some other way that they could spend money that gives them at least R units of utility per dollar, and so they need at least that much value to consider spending money on the platform. We can also handle hard budget constraints by imagining a cost function that is the identity function up to some value b, and in which case it just shoots up to positive infinity. Okay, and we can imagine capturing soft budgets and things like that as well, and more generally like arbitrary convex curves. So again, our result, the main characterization result, is that we fix any mechanism that would be truthful for quasi-linear agents. Right? Then for any setting of the valuation functions v, and any choice of the cost of money curve c, which could be different for different agents, take any agent I and look at any setting of the bids of the others. Then there's always a best response for bidder I, which takes their valuation function vi and scales it by some scalar multiple alpha between 0 and 1. Right? So they always scale their values down. They could choose alpha equals 1, in which case they don't scale down at all, but it could be also less than 1. And I want to point out that this vi is a function, and the alpha I, the vi is a function, and the alpha I is a scalar. Okay, so in general, like more generally, an agent could declare sort of an arbitrary function to the mechanism. What this is saying is that, in fact, to get a best response, you don't need the power to report arbitrary functions. There's always a best response that just takes your original function and scales it by a uniform scaling factor. Moreover, there's a pure Nash equilibrium where each agent bids in this way. Right? So not only are there best responses, there actually is an equilibrium where everyone bids this way. I want to point out that the existence of pure Nash equilibrium requires some delicacy around tie breaking that I'm going to sort of slide under the carpet in this talk. But please see the paper for more details about this. I also want to emphasize that I'm talking about pure Nash equilibrium here. In particular, the model is not a model of Bayesian updating with stochastic valuations. We're assuming the valuations are fixed, and we're looking at equilibria of the resulting game where the agents are declaring their reports to the mechanism. Let me go through an example just to make sure that we understand the model. So let's go back to this example with the apple and the banana. And let's assume that the agents now aren't quasi-linear, but they have this particular cost of money curve where they're quasi-linear up to a payment of 50 cents, at which point it becomes more painful for them to spend money. Right? After 50 cents, the value for spending money is 4 units of utility per dollar spent. Now, in this case, suppose that they reported truthfully, which remember was a good idea for them if their cost of money curves were quasi-linear. If the agents declare choose alpha equals 1, which means that they just report their valuations unchanged, then they would just report those values directly to the mechanism, shown here in red. Remember, the mechanism is this VCG mechanism, which says allocate each good to the highest bidder and make them pay the second highest bid. So these are the bidders that win. Each agent ends up paying a value, which is the second highest bid on that good. Now, the payment of, say, the pink user is now 1, and we can look up on this curve how much disutility that generates for them, which we can see is 2.5 units of disutility. And so if we look at the utility they get from this outcome, well, they each get 2 units of utility from the good they got, but they lose 2.5 units due to their payment, right? This is the disutility from their payment, which is less than 0. So certainly this isn't a best response for either of them, right? They'd each be better off actually not participating in the auction at all. They could have instead each scaled their values down by, say, half, right? By which I mean, for the pink user, they would take their value for the apple and declare half of it, and the banana and declare half of that. Then the values that they declare the maximum are these in red. We can go through the same calculation. The same agents will win, but the payments are now less. And we can look up now on the curve, and the disutility from payment is actually much smaller now, right? Because it's below this soft budget of 0.5, they each actually just suffer 0.5 units of disutility for that money that they spent. So they each get positive utility, 2 units of utility from their from what they got, 0.5 from what they spent. And actually, you can see that this is an equilibrium as well, right? So for example, the pink user could bid higher in order to, say, win the apple, right? They could bid more than 1 on the apple and win it. But if they did that, they would have to pay at least $1 for the apple, because that's what the purple player is declaring on the apple. But their disutility for spending an extra $1, given that they're already spending 0.5, would be 4, which is higher than their value for the apple. So they wouldn't want to do that. And similarly the other way. So actually, this is an equilibrium. Now, it turns out it's not the only equilibrium, right? There are other scaling factors that work as well. For example, suppose the pink player scales their valuation down by 1/3, and the purple player scales down her valuation by less, right? By, say, 2/3. Then these red values are what gets declared to the mechanism. And we can see what would the second price auction do? Well, the purple player certainly wins the apple, right? Because 4/3 is higher than 1/3. But there's a tie on the banana. Either way we resolve that tie, the price on the banana will be 2/3. Okay. So let's imagine that we break the tie by sort of randomizing 1/3, 1/4 to the purple player and 3/4 to the pink player, and have them each pay their corresponding fraction of the price. Well, then one can work out that each player is actually paying 0.5 here, just like in the alpha equals 0.5 case. And if you work through the utilities, you get some quantities which are still positive, but neither player in this case is actually willing to bid higher because the marginal value, like the cost of spending more money, is so high per unit, right? That even though the pink player has a much higher value per unit of the banana than the purple player, they're not willing to spend more to get to sort of break the ties more in their favor. So in fact, we get an equilibrium here as well. And so there are multiple equilibria of this game, and not all equilibria result in this good outcome where each player gets the item that's most valuable to them. What our result shows is that all equilibria have this form where there are always equilibria of this form where the players are declaring these alpha values, right? So they're scaling their valuations by some uniform scalar alpha. And moreover, as we'll show a little bit later, these can differ in the total welfare generated under an appropriate metric not by too much. So I want to just quickly go through the intuition for how this result works. And I'm going to focus on this best response part, because once we know there are best responses of this form, it turns out that showing that there is an equilibrium uses reasonably standard tricks from like the theory of fixed points. But sort of the real meat of it is showing that there always are best responses where you scale your valuations by a constant factor. And so to show how these best responses look like, first we want to analyze what these mechanisms look like from an individual user's perspective. So from a user's perspective, what are they doing? So they have various reports they could make to the mechanism. And each possible report generates some outcome and some payment. And so we can plot this on a graph, right? So where a point on this graph generates a certain amount of value from the outcome, from the allocation they get, and a certain payment that they have to pay. We could plot out all the different points that correspond to all the different reports. And we notice that there's a frontier, right? So possibly by randomizing between reports, a user can sort of pick the best possible way they could spend a certain amount of money. And so certainly at equilibrium, right, they would choose, if they're going to spend some amount of money, to select a point on the frontier, because otherwise there's something else they could do that's strictly better, right? So really the mechanism, what it's doing is it's generating this frontier of possible outcomes, which is payments per, values that they could obtain for any given payment. And because you can have this randomization over outcomes, this won't necessarily be a concave function. So now the optimization from a bidder's perspective is that they're going to look at this value that they could get from the mechanism, which is this red curve. And they're trying to balance that off against the convex disutility for spending money. So the optimal way to bid will be the way that maximizes this difference, right? In this case, in this picture, it would be this star. And so our claim is that this optimal bid, this report that generates the star point, will correspond to a bid that takes the valuation function and scales it by some alpha. Well, so why is that true? Well, I want to point out that if these curves, because I have a concave function minus a convex function, it's actually going to be optimized at a point where the slopes are equal of the two curves. Let's call that slope R. Now, my claim is about a report that generates a point on the red curve, which is actually completely independent of what's going on with this blue curve. So in particular, let's imagine a hypothetical scenario where I have a hypothetical bidder whose value function is just R times P. Their disutility for payment is just R times P. Well, note that then this star point is actually still utility optimal, right? Again, it's the point where the derivatives of the two curves are equal. Well, what is the utility that this hypothetical bidder gets? Well, it's the value of the outcome minus the disutility for payments, which is R times P. Well, the utility function, like the strategic behavior of a utility function, is invariant under different scalings of the utility function. So strategically, this is completely equivalent to an agent who is facing a value function that's scaled down by R, and the payments are just P, quasi-linear, right? I just took my utility curve and divided it by R. And the way the agent behaves is not going to change if I just scale. It's just changing the unit in which utility is measured. But notice now that this utility that I've described on the right here is actually quasi-linear. But I started with the assumption that this mechanism we're looking at is truthful for quasi-linear bidders, which means that for this hypothetical bidder, it must be optimal for them to report their true valuation in this scaled world, which is just value divided by R. Well, this is exactly what we were hoping for, right? So now we're saying is that it's always, you can generate this point on the red curve by declaring a report, which is just your value times this alpha, which is 1 divided by R, the slope of this point. Now, that's the high-level idea of the argument. I want to make some notes. First of all, I've been thinking about all this to this point in this case with, say, additive valuations. But we didn't make use of any properties of the valuation function in this argument at all, really. So in fact, this result holds for arbitrary valuations on a very broad class of social choice problems, sort of similar to VCG. It does require some technical conditions like measurability and convexity of the outcome space and so on. See the paper for more details on that. I also want to point out that this proof is glossing over a bunch of edge cases around tie breaking, right? So I assume, for example, that there's a unique point where the derivatives are equal, which really has to do with, when I have a tie at a certain bid. If I handle ties more carefully, you need to handle things like discontinuities in the curves. See the paper for more details than that. But this simple sketch gets the main ideas. Great. So now we know something about the structure of the equilibria. Let's talk about their allocations. In particular, we might wonder whether the allocations that occur at equilibrium are approximately efficient in the economic sense of generating good welfare. Now, we need to be careful here, as I mentioned before, about how we define welfare, because we're outside the quasi-linear setting, and values are measured in notions of utility rather than dollars. It's not even clear how to trade off the utility of one agent for another. So here, what we're going to do is we're going to take a notion of welfare that really, dives in on this idea that what we can learn about an agent's utility, their value from different outcomes, is how much they're willing to pay, right? Because money is the unit by which we're learning. And so what we're going to do is we're going to write down the agent's willingness to pay for an outcome, this Wi of xi, to be the maximum amount that that agent would be willing to pay to the mechanism to get xi as an outcome, as opposed to getting nothing, getting a null outcome. Okay, so if we give them a take it or leave it offer of xi or nothing, Wi of xi is the maximum amount they're willing to pay in order to get xi. And notice we can just read this off of the curve here. It's basically the amount that the agent would be paying so that their disutility from that payment is equal to the value they get from the outcome. Okay, so we'll say that the transferable welfare is the sum of everyone's willingness to pay for the outcomes they get, the allocations they get in our outcome. And we can think of this as, the agent's collective willingness to pay to sort of implement the mechanism's outcome. Now I want to notice that this generalizes the notion of standard welfare when bidders are quasi-linear, right? Since the willingness to pay for an outcome in that case is just the value. It also generalizes the notion of liquid welfare that's used when analyzing budgeted agents, which is the minimum of the value and the budget, but applies to these more general curves as well. So now suppose the valuations are additive, and let's go back to our example where we're using the VCG mechanism, which is just second price auction per item. Then what we can show is for any valuation and cost of money curves and any equilibrium alpha, which we remember we know exists from our previous result, the allocation that is obtained has transferable welfare at least half of the transferable welfare of any other allocation, right? So this is a price of anarchy style result. The transferable welfare of the result of the outcome we generate is at least half of the optimal transferable welfare, in the worst case over all equilibria. I'm not going to have time to go into the details of that proof, but the basic idea is shares similarity to price of anarchy style results for welfare for simultaneous second price auctions, if you happen to be familiar with that literature. But please see the paper for more details. So to sum up, we're analyzing here the robustness of mechanisms that are designed for quasi-linear agents, in particular when they're deployed in environments where the agents might not have linear value for money. We show that in those settings, agents scale their valuations by uniform factors at equilibrium of play. Moreover, we show that under a reasonable notion of welfare, which we call transferable welfare, we have a price of anarchy result where we get at least half of the optimum at any equilibrium. And as I mentioned before, we also have some results about revenue if we augment that second price auction with reserve prices, but please see the paper for more details about that. In terms of future directions, our welfare results are specifically for additive valuations. It would be great to sort of generalize this and think more broadly about what outcomes can occur at equilibria in general through social choice problems. Also, these are all resistance results. In particular, it'd be interesting to understand whether equilibria can be computed. For example, if we happen to know the form of the cost of money curves that the agents have. That's it. Thank you very much.